And this should say you are recording. All right, so we are recording. And now I'm going to share my screen. Maybe. Enter full screen. What? Oh, that's why it's going on the wrong thing. There you go. I think it's this one. All right. If I do that, y'all can see that. All right. For those of y'all on Teams, you guys should be able to see that as well. Yeah.
Yes, sir. We see it.
All right. So what I noticed this morning is the mic is kind of weird, so I'm going to try to stay away from the mic. So I'm going to kind of talk at the front of my class, but hopefully it doesn't sound really horrible on your end. All right. So the first topic in your table of contents is nature of matter. Y'all ready? All right. So this is the beginnings of electronics. This is not digital electronics. This is the very beginning, so that you understand where we're going with this. Okay. So I've got to come over here and click through. Yep. Maybe. Oh, it's a scroll. Okay. I don't like this, so I'm going to undo that. I'm going to download that. And y'all all have access to this, so if you wanted to, we're not doing architecture. All right, now I'll go back to Teams. I don't even know if what you guys can see, but then I'm going to stop sharing, and I'm going to go back to sharing that. Okay. All right, can y'all see that? Okay, sorry for the weird sound effects if y'all are hearing that at home. This particular PowerPoint, they embed some sound effects there. Right, can you see it over here? Can you see that? Okay. All right, so something you should notice, it's from UNT. This is from their college program for electronics. So just so you're aware that this is a college course still, so we're all dealing with content that they would be doing with y'all at a college level. So nature of matter, yes, it works. Oh, so I don't have to go back to my desk every time I need to change. This is what we're going to talk about: terms and definitions, location of atomic particles, inner and outer orbits, random drift of electrons. You don't have to write all this down. This is just what we're going over. Okay. Oh. And then law of electrical charges. Here are some definitions that we do want to write down in our notebook. So these are basic terms and definitions that you guys may have already seen if you've had any science classes. You should have seen what matter is, what an atom is, what elements are. You may or may not have seen what a compound is. You should know what a molecule is, and then what mixtures are. So I'll kind of go over that with y'all, but put them in your own words. Make sure that you understand what each thing is. Don't get your atoms mixed up with your molecules. And so those of y'all that are here and at home, normally I would wait for y'all to kind of write all this down, but more than likely I'm not going to give. Some of y'all might have a different speed of writing, and I can't really tell who's done and who's not if you're at home and you're here. So I'm going to give you a few minutes to do stuff, but if you don't finish, it's okay. The PowerPoints, you have access to them at home. You can always go back and add into your notebook and finish up what you class. So, but basically matter is anything that occupies space. That's all you really need to write down. An atom is the smallest unit of matter, or the smallest component of matter. Elements are matter that are composed of identical atoms. Compound is what you have whenever you have different elements that are joined together, usually through some sort of chemical reaction. The molecule is a basic unit of a compound. And then a mixture is substances that are together but not joined chemically. So they are still substances that are together but not actually one compound. It's a mixture. My next period? I don't have anything. Okay, I'll come back. Okay. I'll be here. Thank you. All right, and again, just make sure that you get the gist of what each thing is. It's not necessary to write word for word. And we're not writing everything in each PowerPoint. Just the stuff that I'm kind of making sure that you understand before we move forward. Otherwise, I would just print it off. PowerPoint, so. It's not really what this class is about. We're not trying to make your hands hurt from writing. It's just making sure that that content's in the notebook. Okay, everybody good with that? Again, if I go too fast, it's okay. This is recorded and it'll be up on your Canvas. And the PowerPoint is on Canvas. So everything we're doing is already going to be on Canvas for you all. So you can go back and watch if you need to, or go back and finish what you didn't get. Here we go. Here's some more. Electrons, protons, neutrons, all the stuff that you guys should have seen by now in your science classes. Free electrons, ions, and charges. In fact, let's switch to my mask so that you guys, I'm not muffled when I talk. Oh yeah. Now, my face. All right. So, electrons. These are negatively charged particles. That's what you need to know. Electrons are negatively charged particles. Protons, positively charged particles. A neutron is an uncharged particle. Free electrons are any of the particles that are in the outermost orbit of an atom. This is the very furthest away from the nucleus. That is a free electron. Free electrons are going to play a huge part in electronics. That's why we go over this. Free electrons are also called valence electrons. So in some cases on quizzes or terms, you might hear them labeled as valence electrons and not free electrons. An ion is an electrically charged atom. And the charge is either a excess or a deficiency of electrons, depending on what we're looking at as far as the atom is concerned. It's gonna be fun. Electronics is fun. Does everybody like science? Good. Good. Science and math? Anybody like math? Kind of? Good. Yes. It'll be me because I think I'm the only one. Y'all have to let me know if there's people waiting. And if there's anybody has any, if you can see the comments, you'll have to let me know about that too. Let me know to let me in, please. Oh, you made it. Okay. So are y'all still seeing what I'm showing? Right? Y'all are still seeing the PowerPoint?
Yes, sir.
Okay. How do I get back there? Oh, never mind. Figured it out. Maybe. Come on. There we go. Oh, it started over. That's not cool. Okay. So those are your definitions for this particular one. There's not a whole lot of times where we're doing a lot of definitions, but in this first couple PowerPoints, there are a lot of definitions that we have to go over. So this is an example. You don't need to necessarily draw this in your notebook, but you can sketch it if it helps you out. But basically, this is what an atom looks like and how the particles are moving or how they're sitting on that atom. You can see in the center there that you've got your nucleus that has your neutrons and your protons. And then the rings that go around the nucleus have your electrons floating around. Okay? And that's basically what the atom looks like. So if you're sketching it, you can sketch a crude drawing, just a circle, put your positives, your negatives, or your positives and your neutrons in there, and then your electrons floating around. We're going to talk about the electrons here in a second. All right. Periodic table of elements. We will discuss how that works and how these elements actually work with electronics at a later date. Okay, so inner and outer orbits. So basically, your first orbit will contain 2 electrons, and that's the max that it can handle. The second orbit, it contains 8 electrons, and that's the max that it can handle. Third orbit, 8, so on. And you can see the number pattern down there at the bottom, 2, 8, 8, 18, 18, and then it keeps going from there. We're not going to get any further than the first ones, so it's not going to be that big of a deal for us in this class. When you're in chemistry, you're probably going to need to know more, but in this particular class, we don't get that far. So the outer orbit is the one that we're really concerned with. The inner orbits are going to contain their maximum count no matter what. They have no free electrons. The outer orbit is the one that's going to have the free electrons, which means it's only going to be partially full. The outer orbit won't have a full amount, the full amount. It might, but if it does, then it's a different kind of element, and we'll talk about that. But anything that's on that third or outer ring is going to be what we're looking for as far as elements are concerned. Okay. Random drift. This is another definition you probably want to know. Random drift of electrons is the movement of an electron from the orbit of one atom to the orbit of another atom. Okay, this happens naturally. So that's random drift. This is when you're not forcing it to jump from one atom to the other. This is where electricity is coming from. Make sure you get that. All right. So, random drift is when an electron in the outer orbit jumps from one atom to the outer orbit of another atom. That's basically what it's doing naturally. This isn't something where you're trying to push or heat up an electron and make it jump like that. That's not what we're doing. This is a no controlling force applied. It's all natural. All right. Law of electrical charges. This is something you guys need to make sure you know. If it's a like charge, they are going to repel away from each other. If it's a different or an unlike charge, then they are going to attract. So protons are going to attract to electrons and vice versa. But electrons will repel again away from other electrons. And again, that's important for how electronics works. We're going to kind of tie everything together so that you understand how electricity is working. Am I going too fast for y'all? Too fast? Yeah. Right? Okay, so here's my issue. The reason why I'm going fast is because I have to upload these to YouTube. And YouTube tried to give me a limit of 15 minutes before, and I was like, this isn't working. So the last one, it let me do a 30 minutes. So unless I'm going to stop recording and restart recording each time. The first couple of days, like when I teach, like it's going to be like I'm teaching the entire period. Later though, like after the first week or so, 2 weeks, we'll be able to I'll be able to explain it, and then you'll be able to do something. So this is something we should have done first week. Do what? I don't know. I tried to upload this morning, and they said my video was too long. You what now? Have to verify my account. How do I do that? Go into my settings. All right, I'll mess with that this afternoon then, because I need to be able to put up longer videos. And I downloaded the video editing software, but I'd rather not have 10 videos for one subject. So, okay, we got that. That is the end of that PowerPoint. All right. So, not a whole lot that we had to write down, but there was some information there. All right. I'm going to go back here. In your Canvas, those of y'all that have your Canvas open, you should now be able to see the next one, which is nature of electricity. And in Teams, I think I have to stop sharing and then reshare. Y'all see the nature of electricity, those of y'all that are there? Okay. So then I think I have to go back and reshare nature of electricity. Right. So now do y'all see that? Do y'all see the nature of electricity one? Yeah? Okay. So that was the first PowerPoint that we went over. Oh, we get more sound effects. Yes. So in your notebook, in your table of contents, underneath the first one, you're going to put nature of electricity as the second one. And then if you didn't fill up a whole page for your set of notes, you can put down the following page, or if you're going to continue on that page, just make sure that your page number in your table of contents still says 1, so that we know it's still on page 1. Does that make sense? Okay. Because I know there wasn't a whole lot we had to write down on the last one, but there was some definitions that might have taken up some of that page, or the majority of that page. So the idea here isn't that it has to be a certain page number. That's not important. What's important is that you keep track with your notebook and your table of contents and put the correct page number in your table of contents for the content we're going over. Nature of electricity. So what was the first one? Nature of matter, and now we're in nature of electricity. And again, I'm going pretty fast, so normally probably wouldn't get all this done today. But I know we're pretty far behind, so it's good. Everybody ready? All right. Nature of electricity. Okay. In this one, upon completion of this assignment, the student will be able to explain atomic theory, electricity, and the properties of various materials. So now we're going to kind of get into how electricity is going to work. Specific objectives, we're going to be talking about the relationship between elements and compounds. We're going to be talking about a model of an atom, which we've kind of already seen. Concepts of atomic weight and atomic number. State of the law of charges and explain some examples. Electric current, voltage, and resistance. Two theories of current, direction. Distinguish between conductors, insulators, and semiconductors. So we're going to go over a lot in this PowerPoint. Oh. You don't have to write all this down again. This is just our objectives and what we're going to cover. But some of this we'll have already covered from the last PowerPoint, so we can skip some of it. So compounds and elements, we already have these definitions in our last PowerPoint. So you should already know what an element is. You should already have a definition for a compound. Okay. Atoms, we should have that also in our notebook already, because we did this on the last PowerPoint. We won't need to cover that again. Periodic table of elements, you probably need to write this down because we didn't do this. But it's arranged or organized by each element's atomic number, if you didn't already know that, which probably did. So make sure that we know what that is. Number of protons, yes. Atomic number refers to the number of protons or electrons in that element. If for whatever reason you missed that day in 7th grade science class, this is how periodic table is arranged. It's arranged by how many protons or neutrons or electrons it has in each element. Good. Okay. Current, voltage, and resistance. These are going to be definitions you probably don't have yet, so we need to make sure we get these in our notebook. Current is the movement of electrons in a conductor. So current is the actual movement of those electrons. Voltage is the force that's moving those electrons. So the force that's pushing them. It's the push. The voltage pushes the electrons through the material, and that's what's creating the current that makes all of your devices work. Resistance. Resistance is the opposition of that flow or of the current. So it's what's pushing back or keeping the current from going as fast as it wants to. Most of the time they call resistance control. So it's kind of what controls the current. By adding or reducing resistance, you can change how much current you actually have flowing through a device. Very good. All right, so that's your current voltage and resistance definitions. We have AC and we have DC. Direct current, or DC, only flows in one direction. And AC, or alternating current, moves in both directions. So it'll go in one direction and then it comes back the other way. That's why AC is so dangerous, because if you get shocked by an AC current, it's going to shock you over and over and over and over and over again. Whereas if you get shocked by DC current, it's basically a shock and then you're done. That's why you have to be very careful dealing with AC current. Alternating current. I don't think they write that up here. That's why I didn't want to move forward. So AC is alternating current and DC is direct current. It alternates directions. That's how you know. That's how you can remember. It's alternating directions. It's going one direction and turns around and goes the other way. Most of the time, if somebody gets hurt, it's usually from AC current. So. Which we don't really deal with in this class, just so you're aware. We don't really deal with much AC current in the class, so if at all. We're dealing with DC. Very good. All right. Conductors, insulators, and semiconductors. Okay, a good conductor of electricity is anything that permits the free flow of electrons. So this will allow electrons to flow through it easily. That's a conductor. Okay. That means that there's not going to be something that's going to keep the electrons from going through it. It's going to allow electricity to pass through. Poor conductor obviously will not allow electrons to flow. Semiconductor is one that limits the amount, or the amount of flow, but will allow some. And we're going to kind of go over the majority of how you would tell what's a conductor and what's not a conductor, that kind of thing, which most of you will probably already know, but just in case. Any of y'all have any ideas on how you would know if it's a conductor or not? Do what? Periodic table. Yes, absolutely. That's how we're going to find that out. Did you already know that? Is this basic knowledge for y'all? It has to do with valence electrons because it has the way one will have exactly it can be like that, yeah. We're going to go over it though so everybody knows. I have found different PowerPoints that explain stuff and then created different PowerPoints that help, or at least somewhat help. So the idea is that you understand. So we're going to try to get you to understand what's going on. So here we go. Conductors and insulators, here's some examples. Conductors, copper, iron, steel, aluminum. What do all those things have in common? They're metals. Okay? Most metals are going to be good conductors, most of them. There are better conductors and worse conductors, and we'll talk about that in a minute. One of the things you can see down here is damp earth, because if the ground is wet, that allows the salt water to actually mix in with the material, and that makes it a good conductor. But the water has to have salt in it in order for it to be a good conductor. If there's no salt, then there's no material for it to go through. Like the straight actual water does not conduct electricity. It has to have salt in it. Insulators like glass and mica, porcelain, these are all materials that do not have the conductive material or conductive traits. So they will keep electrons from flowing through. Now you can push hard enough and if you get enough voltage, you can end up pushing that current hard enough to go through these types of materials. But then you're talking about very dangerous amounts of current in your circuitry. So normally we don't try to do that, but you notice one thing in there, air. If you look at the air, air is a insulator. Yes.
So then, how does lightning occur?
Exactly. How does lightning occur? So if we have air, there's a big gap. So what's happening with the lightning? This is why lightning is so dangerous. Is it is it's a huge amount of push, tons of voltage pushing that lightning bolt to go through the air to go strike something. So that's why when it hits something, normally catches fire, or that's why we have grounding rods to try to run it straight into the ground, that kind of thing. But that's what lightning is. Lightning is just a massive amount of voltage pushing that current across air. And so that's why it's so dangerous. But so with the massive amount of push, yes, it'll cross air. And if you've ever seen, what's that machine where you can, the Tesla coil, where you can see the spark jump across. Right. Right, and then you've got electricity in the air, and you can see it'll pass through, but it also uses a lot of voltage as well. So semiconductors, selenium, silicon, germanium, most of these are some sort of compound material that's been completed together using that particular type of element. They work great because you can control how much electricity by changing the different traits for it, and you can kind of turn it into whether you want it to be a conductor or you want it to be an insulator. You can kind of control that, and so that's what you'll find in your processors and things like that for your computers, because they can control it, whereas they wouldn't be able to control something that was straight metal. So okay, I think that's it for this one. You can see these PowerPoints are kind of quick. All right, so we have done what time is it? 2:42? I think we're supposed to get through with the third one today, and then we should be done. So the next one is called the atom and Ohm's law. And if you have your Canvas open, you may have to refresh, but it should be there now. And then I just got to figure out how to put it back on Teams. So I got to stop sharing. Everybody online able to see all this that we're going through?
Yes, sir.
Yeah, and I'll be posting it to Canvas. So you guys, if you're missing something, always go back. I just have to figure out where that one is now.
Hi.
Hello.
One.
Okay, how do I get out of it? Okay. It's weird. Now you can hear people talk, but no one was able to, like, does it not let you guys talk whenever I'm showing my screen? Does anybody know?
This is on Canvas, right?
This is all going to be on Canvas, yes. And actually, it should be on Canvas right now, actually.
Also, this recorded. This being recorded. I mean, now it's recording.
Yeah, the recording that we're doing right now will end up on Canvas in probably the next hour or so.
Yes, sir.
Okay, so this is the last one we're doing today. This is the electric circuit theory. Can y'all see that? Okay. All right. And this one kind of explains everything so that you can see how electricity is happening. So, electric circuit theory. This is the basis of all electric circuits. So now that we know where the atoms come from, or what kind of atoms we're looking at, and how the atoms have valence electrons, we're going to see how the valence electrons matter in what we're doing. So in your table of contents, electric circuit theory, you can put the ohm in Ohm's law if you want, but the truth is it's electric circuit theory is the name of the PowerPoint that we're really going through the topic. Because this is what we want you to understand. It's going to be fun. All ready? Everybody? All right. Here we go. So this is just another example of what the atom looks like. It's less crude than the last one, but you can kind of see that there's a nucleus in the center, and it has neutrons and protons in it. And then you can see that your electrons are in some sort of orbit flying around that nucleus. Okay? So that's basically what we're looking at as far as what an atom looks like. So electronics is all based on the electrons in the valence orbit, or the valence electrons. So when we're looking at an element, what we're looking at is the number of electrons, or the electrons that are in that farthest orbit, or the one furthest away from the nucleus. Those particular electrons are not tied to get to that particular atom very tightly. So they can kind of fly off if we need them to, and they will whenever we're using them, depending on how many are actually in that valence orbit. So those ones on the very outer edge are the ones that are easy to move to come off of that particular element. That makes sense? Okay. So the ones on the inner rings are all too tight. They're basically being held in by the other ones in the further out orbit, so you can't fly off as easily. With the force, you probably could get them to all do that, but that's not what we're trying to do. Okay, so conductors. They have 3 or less electrons in their valence orbit, or they have 3 or less valence electrons, however you want to say that, but that's what we're looking for. So if you look at the 3 examples on the page, each one of those, copper, silver, and gold, if you look at the valence, or the number of valence electrons they have 1 valence electron in each one. Okay, so these are going to be your different types of wire, and that's usually why you see everybody use copper wire, because copper wire has only 1 valence electron in it. Copper only has 1 valence electron, so that makes it a very good conductor of electricity, because that valence electron can come off very easily. So anything with 3 or less electrons in the valence ring is a conductor. That's basically what you need to make sure you write down. And I don't know if I'm loud on that. I feel like I'm yelling, or maybe it's just echoing when I get this mask on. But this is what you need to make sure you write down. 3 or less electrons in your valence shell is a conductor. Okay? Does everybody understand that? Where you only have 1 valence electron in each of these particular elements. And that's what we're looking for as far as conductors. All right. Top 4 conductors. You've just seen 3 of them. Copper, silver, and gold are 3 of the top 4. The top one is going to be a superconductor, where if you guys have ever seen any of the, everybody's seen Iron Man, right? When he creates the new element, in the Iron Man series where he's sitting in his room and he makes the new element. That's what he's doing. He's creating a superconductor, or at least that's what theoretically he's making. Superconductors obviously will work much better than a natural element that you find in nature. So we're going to talk a little bit about them, but not very much. All right. So those are your top four: gold, silver, copper, and they also are priced differently. So gold's probably the most expensive.
Isn't copper like the best conductor? Or is it the most widely used?
It's the most wide. Copper's the most widely used because it's the cheapest of the good ones. No, but gold is much better. And if you get into higher electronics, higher priced electronics, that you're looking for sound, like if it's a sound issue, like the sound clarity or the loss of signal, that you don't have any loss of signal, gold is what everybody wants to use because it will be, it's more expensive, but it is the best as far as signal loss. You don't get that. So a lot of people will use gold, but you'll pay for it. And so they try to do gold plating and things like that so that it's not so expensive. But superconductors are more expensive, just so you know. There's a huge jump in price between the two. Okay, so superconductors, we're kind of go through it, just but this is really the only time we talk about it. The HTS, or high temperature superconductors, basically get super hot, which means they have to stay at a temperature that is extremely cold. So in this particular case, we're looking at a 39 degree Kelvin. You can see, I think it's floating, right? Isn't that what it's doing? I think there's a material that's floating above it. But the actual object is this. Anyway, but it can carry the same amount as copper, the copper wire that's 100 times thicker. So this will be doing a better job by 100 times of what you would pay for copper. So you could potentially make that copper wire 100 times thicker and get the same kind of conductivity out of it, but you know, that's not really feasible for actual electronics. But which I don't know if they're still doing that, but they, you know, they had that picture of the high-speed train on the last picture, on the last slide. And they were supposed to be doing a high-speed train from Houston to Dallas, but I don't know that that's still happening or not. But they would be using this superconductive material as the material to carry that much voltage. I think Japan has one. You know, we're talking about extreme speeds, so it's kind of cool. But you have to be able to conduct that much electricity using some sort of material, and copper wouldn't have handled it; it would have just melted. So that's why you have to get a thicker amount. And that's also why, if you look at that picture of the braided or the stranded copper, it has a lot of different strands. So there's a lot of small little pieces of copper, but they're all like twined together to make it a thicker piece. However, you can still burn these. These end up, if you get a big spark, it'll start cutting through, and it'll burn like half of it, and then you've lost half of your conductivity. So then they start going back to solid copper when they need a higher temperature or a higher current. Anyway, that's semiconductors, which we won't be talking about very much in the class because we can't use them. We don't have that kind of money. So we're going to look at insulators next. Insulators are going to be any material that has 5 or more electrons in their valence shell. So here's an example. Pure H2O is an insulator. When you put salt in it, it turns into a conductor. But here's 2 examples: oxygen and neon. And if you look at the valence ring on these, this oxygen has 6, neon has 8. Right? So, so y'all have any questions about any of that so far? Okay, so something that y'all, that we were talking about before with the lightning, there's neon signs that you see out basically all over the place, which you would say, well, how do you get the neons to light up? What they're doing is they're pumping a lot of voltage through those in order to make that electricity flow through neon, and that's how they're getting neon signs to light up. So that's kind of what the idea is. The same kind of idea that you look at for lightning. It's passing through that material, but the voltage is super high. You get to do that. Everybody get that? All right. So 5 or more electrons in your valence shell is an insulator. All right. Semiconductors. Basically, every element with 4 electrons in the valence shell is going to be a semiconductor. So basically, you can play with their chemistry in order to make them a conductor one instant, and then an insulator the next. This is how we're going to be able to use majority of the electronics, because a lot of electronics, actually all of electronics, really deals with a switch being turned on and off over and over and over again. So that's what electronics is all about. So we'll be learning a lot of, we'll be using a lot of things that require semiconductors. So a lot of times you'll see IC chips or processors or things like that, RAM. I'm sure that anybody that's dealt with building a computer, all of those types of chips are all made out of a semiconductor material, which is how we're able to do or get most of the modern electronics that we have now. So like cell phones, computers, all of that. We had to have semiconductors in order to make all that work. Otherwise, none of this would work. But there's the major ones that they use are silicon and germanium, and that's why it's called Silicon Valley, because that's where they started the computer business and processors and all of that. So it all came from that area. So that's where it all started. Does everybody get it? Okay, that's semiconductors. So here's your periodic table, and if you look, all of these different elements are placed in a specific way on that table so that you can see which ones kind of fit as a conductor and which ones fit as insulators and semiconductors. All these ones in orange are going to be your semiconductors, and then anything off to the right of those are going to have less or have more valence electrons, which make them insulators, and anything to the left of that is going to be your conductors, because they have less valence electrons in it, in each element. So that's kind of that's how you can look at a periodic table and be able to tell, oh, I'm looking for a conductor, but all I have is, zinc. Is zinc going to be on the right side? Am I going to be able to use zinc? Well, yeah, it is a conductor. Probably not the greatest conductor, but it is there. And if you look and try to find, got zinc close to the copper, and then underneath that is silver. So, so it's pretty close to the same kind of idea or the same kind of quality that you would get. Probably not quite as good, but that one row or column has the 3 main conductors in it. So kind of what we're looking for. In the orange column there is your semiconductors, and then everything to the right of that is insulators. And as you go further right, you'll see that they start getting better conductors or insulators. But that's how it is. Everybody get that? Now that you see it on a periodic table, you should be able to see how that's kind of working. All right, moving forward, new words. Got some more definitions to write down. Load. Load is any device that uses electrical energy to perform a task. So basically anything that needs a battery or a plug. Anything that's using electrical. That's what we call a load. Most of the time it's represented as like a light bulb in most electronics, but it can be pretty much anything that's a device that uses electric current. All loads have a value of resistance. That's important. You can jot that down. We'll explain that in just a minute. What time do we get out of here? 12 minutes? Okay. So like I said, the first couple of days, I'm like talking the entire time. And it starts to be more of I explain it and then you go do it. So they need to have electricity pushed through them in order for them to work. The higher the load, the higher the resistance. So if for whatever reason you're making a circuit and your light's not very bright, that's because the load, your light bulb, is too high. So you need to increase the amount of voltage or decrease the amount of resistance in order to get that light bulb to be brighter. So when you go to buy light bulbs, you see that they're listed by wattage, so like 40 watt, 60 watt, 100 watt, depending on how that's working. What that's doing is it's reducing the resistance on the light bulb to make it brighter. You can't really increase the voltage coming out of the wall. So that's kind of how it works. Very good. That is load. Transducer is the next one. Any device that turns one form of energy into a different type of energy. So what's some examples? What kind of energy can we get from, or what can we produce electricity from? What do cars run on now? Gasoline or electric current. So they have, and that's a chemical reaction. You've also got things like solar power, where you're taking the light energy from the sun and creating electricity through that. It's converting, it's not creating. So it's converting that kind of energy into another form. Most loads are transducers, and what they do is usually turn that electrical energy into some sort of other type of energy. So they're most of the time they're going to be creating something else, whether it's light or a motor running or something like that. Did you guys enough time to get that? Yeah. Yeah, I think I'm going to stop right here. Okay, so on the next video or the next chat, which will be tomorrow, those of y'all that are face-to-face will be at home. Make sure that either you get on the Teams meet or watch the video that I post, because I'm going to end up posting these. But that's it for today. That's as far as we're going to go. We're going to finish the rest tomorrow. Maybe if I can figure out how to get out of this. There we go. Okay, the title of the PowerPoint is numbered wrong. Yes, I think it's number 4, and it's because I skipped number 3, because number 4 covers number 3. I'm going to stop sharing. I'm going to stop recording because it's been over an hour, and I have no idea if I'm going to be able to get that to work or not.